Hello everyone, we will be presenting our work Doodle Your Keypoints, sketch-based few-shot keypoint detection accepted in ICCV 2025. Although it is easy to annotate a few key points on a photo, the major challenge of few-shot key point learning is the scarcity of suitable photos for support. Like their supervised counterpart, few-shot key point learning can be extended to multi-class images beyond just different key points on the same class of objects. However, this adds another layer of challenge due to the class-level domains between training and test data. On the other hand, collecting even a few photos become a daunting task due to privacy, copyright, or in case of rare objects or animal species. Sketch provides an easy alternative to photos as they are easy to collect and annotate. For example, an organ of a rare animal species may be difficult to photograph, but a field expert may be able to draw and annotate the same using a touchscreen device. Overall, Sketch provides a source-free cross-modal setup that comes with its unique challenges. The abstract nature of sketches allows the user to depict the same subject with varying styles. Training data for keypoint annotated sketches remain a challenge. The domain gap between sketch and photo is non-trivial as we have no instance level pairing between support and query due to the definition of few-shot learning. We observe that edge maps are very close to simple line drawings and can substitute sketches as synthetic data. Different edge detectors can also simulate different sketch styles. Based on this, the proposed framework considers a few approaches to the solutions. We disentangle the user-specific styles from the sketch content. Beside using the edge maps as the synthetic data, we use augmentation techniques to extend existing key points, and a prototypical domain adaptation is used to address the sketch photo domain gap. Our framework closely follows the prototypical setup introduced by Liu et al. First, the support sketch and the query photo are passed through the image encoder. Next, we use Gaussian pooling on the support feature map separately for each key point. A two-dimensional Gaussian distribution centered at the key point location is multiplied element-wise on the support feature map, and then the entire feature map is aggregated to obtain the corresponding key point embedding. The key point embeddings are then destylized by passing through the destylization network. Next, we formulate the support keypoint prototypes by averaging the corresponding keypoint embeddings across all the support sketches. Once we obtain the support prototypes, they are correlated to the query feature maps using a feature modulator. The feature modulator element-wise multiplies each keypoint prototype with the query maps. Then a descriptor network is used to encode the location information of the correlated feature maps to query descriptors for each of the keypoint prototypes. The only remaining piece of the puzzle is now the localization strategy. For localization of the key points in the query photos, we use a grid-based locator or GBL at multiple scales. First, the query key point ground truth locations are converted into grids and offsets. The entire image is divided into grids and the offsets indicate how far the key point is from the center of each grid patch. The GBL has two components which are used to perform the localization. The grid classifier tries to model the probability of the key point being located in each of the grids from the query descriptor, and it uses a negative log likelihood loss for the classification. The grid regressor corresponding to the predicted grid from the classifier tries to predict the offsets from the center of the grid. The regressor uses an L1 loss for supervision. This entire setup is used in multiple scales at the same time as we use different grid scales to patch the image. The overall localization loss is the total of both classification and the regression losses. Once we have our baseline framework, we look into the sketch photo domain gap as it is non-trivial due to unavailability of instance level sketch photo pairing. To address the domain gap, we use a prototypical domain adaptation strategy. This strategy originally used a bidirectional transport loss that estimates the required cost to transport queries to the support prototypes and support prototypes to the queries. These two transport costs depend on a point-to-point cost and a similarity measure. Although the original bidirectional transport loss was used in unsupervised setting, we compute the query key point prototypes from the ground truth locations, detach them from the computation graph, and use them as a supervision signal. In particular, we use a probability measure of how close the query prototypes are from the support prototypes. Although the original bidirectional transport loss had two terms for two directions for classification task, in case of key point embedding regression, in supervised setting, it collapses into a unified form. Our framework also tries to address the different user styles observed in sketch data by disentangling the same from the contents of the sketch using the destylization network. To aid the destylization process, we imitate different user styles using different edge maps generated from different edge detection algorithms. They vary in sparsity levels, just like sketch, and simulate its abstract nature. Next, our handcrafted destylization network takes care of the disentanglement of user styles using the local key point level information obtained from sketch in the context of global sparsity through an attention-based feature fusion technique. The disentanglement process is guided by L2 losses between the keypoint embeddings of different edge maps. To handle the scarcity of the training data, we use synthetic data and augmentation techniques. We have already used edge maps as synthetic alternative to Sketch. Alongside, we also extend the existing keypoints to several auxiliary keypoints by interpolation. The new auxiliary keypoints are considered on the line connecting two main existing keypoints if they exist within the object region. The auxiliary keypoints contribute towards all losses and objectives. We train and evaluate our framework on two major datasets, Animal Pose and Animal Kingdom. We use edge detectors on the photos from these datasets to simulate sketches. Alongside, we also use a small subset of the sketchy extended dataset to understand how well the framework generalizes on real sketches. We choose a few state-of-the-art key point detection strategies as competitors and adapted them to the few shot setting as required. Apart from these, we also establish a few baselines. B vanilla uses only the localization loss, BDA and B style uses only domain adaptation loss and the distillation loss respectively on top of B vanilla. B full gives us our proposed framework. For evaluation, we use the percentage correct key point measure, where we consider a key point to be detected if the predicted location is within a range of 0.1 times the image width from the ground truth. Here we evaluate our competitors in four settings: novel key points and base key points on each of novel classes and base classes. Here we showcase our performance against the main competitor from which our baseline was inspired. We also compare with additional competitors here. We see our method outperforming all of them in all four settings. As our framework was trained with edge maps instead of real sketches, we investigate how well they generalize on real sketches. We see minimal performance drop, which proves the generalizability of the proposed framework. To ensure the robustness of our framework, we investigate how it performs when we use photos as support. We observe that our framework cannot outperform the state of the art when only photos are used as support. However, we also observe that when photos are used along with Sketch in a multimodal setup, the proposed framework outperforms the state of the art. We also perform several ablative studies to understand and justify our framework design. We performed a loss stripped down style analysis using the established baselines to understand how every loss objective contributes towards the final result. We observe that every loss objective is useful and together they bring out the best performance. We also observe that auxiliary key points boost the performance of every baseline by a huge margin. We experiment with the number of sorts for the few shot setting, and as expected, we observe an increase in performance with the increase in number of support. We also experiment with number of training key points and observe that increasing the training key points improve performance as they provide more training data as supervision. This observation holds true for both main and auxiliary key points. Next, we justify our design choice for the destylization network. We observe that just the destylization loss can improve performance without any destylization network. We also see that the global context certainly helps, but needs to be fused with the local information properly. Here we showcase some visualization of the inference of our few-shot framework on query photos along with support edge maps and real sketches. Thanks for your attention.